Here we see Discovery on the launch pad out there. Everybody talks about how things move so fast in a space program. In our case, it took 2 months to get from T-minus 4 seconds to T0. That's not always true. Fortunately, the weather was just beautiful out there. It was nearly perfect. I think probably the best weather we've had for any of the shuttle launches yet. Here we show the main engines igniting, and the twang, the orbiter moving, was very apparent to all of us in the cockpit. You can see the twang. Those are the bolts firing on the solid rocket boosters. There was no doubt when the solid rocket boosters fired that we were going someplace in a hurry. When we lifted off, we had the heaviest stack that is launched since the Apollo days, the Saturn V back in Apollo, over 4.5 million pounds lifting off. You see the roll right here. The roll seemed dramatic to us, I guess, because we're on the outside of the stack and the real world was out there. It was a lot more dramatic, of course, than the simulator had been. We were actually carrying the heaviest payload by about 10,000 pounds that had been carried by the shuttle. We had over 47,500 pounds of payload we were lifting. You can see the shock wave right here. That's just behind the windows on the top of the orbiter as we're going through the maximum dynamic pressure during ascent. We're actually throttling the main engines back here in 2 stages to get through the maximum dynamic pressure. As you can see, it's a beautiful day. We had separation of solid rocket boosters and a little film over the windows, just like we'd had on all the previous flights, but not objectionable.
We made it to orbit, and we needed to get to work right away because our flight day 1 included deployment of the Satellite Business Systems satellite, and we proceeded on with that task, and the techniques involved were not different from those employed on previous PAM deploys. Here you see the sun shield opening. Of course, the purpose of the sun shield is to protect the satellite from the sun while it's in the cargo bay, and that all was completely normal. My responsibilities in the deployment required that I be in the commander's seat using the forward display tubes. Mike Mullane helped with the PAM deployment at the standard switch panel in the aft, and the rest of the crew was heavily involved in supporting the deployment, monitoring systems, and keeping track of the number of photo, television, documentary requirements that we had. The PAM, as you know, is not particularly sophisticated in terms of its onboard guidance. It requires the orbiter to point it, and it's spin stabilized in a method that you see here. A spin table in the orbiter's payload bay spins the satellite at about 50 RPMs to keep it stable on its way to geosynchronous orbit. In a second, you'll see the deployment of the SBS satellite, and if you look very closely, you can see the camera wobble right at the instant of deploy, and that'll be evident in the picture. We felt and heard that, and it was an appreciable jolt and quite a bit of bang, but we were not surprised. We had heard that from previous crews. There you can see the camera jiggle just slightly, and that was just exactly what we expected. Otherwise, we felt nothing, and it was completely normal. The orbiter systems and the satellite systems performed extremely well, and we were very pleased. The simulation that we have here in Houston is, of course, very good, and both Mike and I commented that we felt we had done this 100 times before. It felt very comfortable to do it in flight, and we just expected it would work perfectly.
On the morning of flight day 2, we went to work on deploying the second satellite, the SYNCOM, and as with PAM, it's a team effort. I was at the standard switch panel in the back again, and Steve was up in the front in the CDR seat. He operated, the SYNCOM is held in the payload bay by 4 motor-driven pins, and he was operating the computer to pull those pins. Steve started a verbal countdown, and at T0, I threw some switches that fired a pyrotechnic device that allowed the SYNCOM to roll out of the payload bay. The SYNCOM is like the PAM in that it's a spin-stabilized spacecraft, but unlike the PAM, it gets its initial spin stabilization at the moment of deployment. It rolls out of the bay with about a 1.5 RPM spin and about a 2 foot per second translation away from the orbiter. The SYNCOM is the first satellite, as Henry mentioned, communication satellite to be designed to be carried strictly by the shuttle. It's going to be used by the United States Navy as a UHF radio communication relay satellite. It was essentially off in the payload bay. It turned itself on automatically at deployment, one of the first things that happened was that white antenna was deployed to allow the ground to communicate with the satellite. And I talked to the Hughes people yesterday. They said it's doing just perfect.
About 15 minutes after each of the satellites was deployed, we got ready to do a burn on orbit using the maneuvering engines, 8,000-pound engine at the back of the orbiter. Give us a little more separation before the perigee kick motor on each satellite fired, 45 minutes after deploy. You'll see the engines ignite here in just a second. After the ignition, you won't see anything while they're firing in the vacuum up there. There's the ignition, and now they're firing. You won't see very much. You'll see the tail off in just a second, and then right after the tail off, you'll see one of our primary thrusters fire just to the right, on the right home spot there. There's the thruster firing.
As I mentioned earlier in connection with the SBS deployment, we had a fairly awesome amount of photo TV requirements on this flight. You see the CDR with the IMAX camera. We were fortunate enough to get some good IMAX film of the deploys and a number of in-cabin activities, and Hank and Mike Coates get the credit for making that all work. One of the first that Henry mentioned was the fact that ours was the first flight to deploy 3 satellites, and here's the third, the Telstar satellite for AT&T. And as with SBS, it was absolutely normal. There were no problems at all, and Mike and I felt very comfortable doing the task. One of the requirements we had was to film using the RMS wrist camera the burn of the perigee kick motor for all 3 satellites. And in a second, we'll show you the perigee kick motor burn for the AT&T satellite. Notice below on the ground the lightning in the clouds, and that was very noticeable, and we're glad we got it on tape to show you. Here it is. And it was so dramatic at night that the lightning on the ground would light up the payload bay. And it took me at least several seconds to figure out exactly what it was that was causing the light. And there's the perigee kick motor ignition. In all cases, the motors burned exactly as predicted, and it's a fairly easy task for the crew to monitor that burn. And as I mentioned, Judy had to position the arm from the cradle position to the observing position after each deploy. And you can see the AT&T satellite on its way to its transfer orbit, which from our point of view appeared to be nearly in the direction of the constellation Orion, which you see in the upper right-hand corner above the Earth's limb. And we were very pleased with that shot. We thought that was quite nice.
Beginning on flight day 1, I started the electrophoresis operations in space payload. Some of the operations included interaction with a microcomputer at the electronics center of the payload, which you see behind me in this picture. The majority of the payload work was with the fluids system module, the large module that you see me working at here. There were several tests that I had to do manually at that module, calibrating flow rates, and also checking to find the presence of the particular biological substance that I was looking to separate and purify in the microgravity environment of space. And here I'm performing some fluid sample collections and using a small kit that was carried along, determining the presence and the quality of that material. The payload operations, although hampered by some problems, went well.
We extended a large solar array wing several times during the flight. This is the largest structure ever deployed in space. It was 1,300 square feet, yet it only weighs 300 pounds. The purpose of the array is to supply electrical power to a spacecraft or a space station by using the sun's energy. A wing this size has about the same capability as one of the orbiter's fuel cells, which is just about as much power as we typically use on orbit. The array unfolded just like an accordion being pulled up from the top by a coiled mast, which you can see in the front. The mast was made out of a fishing pole type fiberglass, and the blankets are pulled taut at 2 extension lengths, 70 feet and 100 feet. Here we have a scan from the aft window up out the overhead window, giving you some idea of how large the array really looked to us as we were doing work with it. While the array was extended, we used the small thrusters on the orbiter to try to excite the mast. We found it to be very stable, showing only small deflections that damped out very rapidly, and we were able to maneuver quite nicely to different attitudes with the array out. Here we're coming across Baja. One of the things that we noticed about the array was that it was translucent, so we could see both the sun and the Earth going by behind it as we were maneuvering. All in all, it was a good flight test for large space structures with potential future use in either space-based construction or in space station operations. And it's also a potential prototype of an inexpensive power source in both dollars and weight of the future for NASA. And we spent a lot of time taking photographs with the various cameras that we had on board of the operations of the mast. Here you see it extended to 100% with the intermediate tension bar, the white bar across the bottom, and it was quite large. Henry trying to take a picture of the top. And in this closing shot, we have a sunset. You can see the sun shining through the array. We were tail sun at that time, and when you see the shadow of the vertical tail on the left bottom portion of the array.
For a new orbiter, we had remarkably few equipment malfunctions. One failure we did have was one of the 3 forward display units failed shortly after orbit insertion. This was really no impact to the flight, but after the satellites were deployed and the OST work was done, we decided to change it out with the aft display unit, which was no longer needed. So we did what we call an in-flight maintenance, or IFM. We broke out the toolbox and changed them out. There are some advantages and disadvantages to making repairs in zero-G. One of the advantages is you can float up into the nooks and crannies that are very difficult to reach on Earth, and they're very easy to reach on orbit. One of the disadvantages is you've got to remember to brace yourself quite well when you're using the tools. It didn't do any good to outweigh the wrench by 185 pounds, zero-G. But we did change them out successfully and had 3 forward display units for entry and landing.
It was along about the same time that we were doing the IFM that we discovered we had the icicle on the dump port. And at this particular time, we were going to go out and break it off. Judy came up and handled the communications and kept me honest with the RMS while we were doing this task, double-checking on the procedures. The ground really did a super job in putting together the procedures to do it. Here's what it looked like as we started the wastewater dump. You can see the size of the icicle on the supply port. Now watch very closely at the bottom, the wastewater dump port, and you'll see that big icicle growing right before your eyes. It grew dramatically fast. I couldn't believe what we were looking at. We immediately stopped the wastewater dump and then spent 2 days with that side of the spacecraft to the sun to try to warm up the icicle a little bit and let it sublime. We were somewhat successful in that. As you'll see here shortly, the size of the icicle was reduced. We took the procedures that the ground had sent up to us to use the arm, poised the arm, and took a look at it. We had people looking out the windows just to make sure we weren't going to bump into anything on the side of the orbiter, but we didn't have to fear because the procedures were absolutely correct. Here's what it looked like the day we went to knock it off. You can see it is reduced in size, but it's still there. We're moving in very slowly with the arm now, and what happened is you move in, you lose sight of it in the camera, so you just have to keep going. If you watch closely now, you'll see a little piece of ice go chipping off up to the top right-hand corner of the screen, and that's when we hit it. There it goes, a little chunk of ice there. Had no trouble whatsoever executing this procedure with the arm. The arm worked beautifully, as it has on all our flights. And when we pull back here, you can see just over the top of the end effector of the arm there, a little black spot. That is the dump port, and the ice is gone. Mike Mullane took this picture out the window as the chunk of ice floated by, and you can see it's a pretty good-sized chunk of ice. We were really relieved to see it gone.
It wasn't all work. Here's Judy and Steve playing a little handball with our flight mascot. Zero gravity was a lot of fun. Here Steve and I were demonstrating some of the physics of the Frisbee deploy that we talked about with SYNCOM. Steve thought this up, got a filter off of our hatch window, and we labeled it SYNCOM, and we floated it there in zero-G, and Steve gave it a tap just like the spring did on the real SYNCOM. and you see that it translates and rotates straight up, just exactly like the real spacecraft, proving that the physics of a Frisbee are the same in zero gravity as they are here on Earth. I wanted to show you a little bit about our food preparation. We carry mostly dehydrated food because we have water manufactured as a byproduct of the fuel cells. Here you see a pack of dehydrated strawberries, and you add 2 ounces of cold water to it and let it sit for a couple minutes, and you got yourself dessert. And that's our water dispenser there that Charlie is operating. He's selected 2 ounces, and he's injecting the water into the plastic container. There's a plastic cover that holds the strawberries and the water inside. After you pull it out of that device, you have to knead it for a little bit to rehydrate the food. This is particularly important for the shrimp cocktail to make sure you didn't get a dose of horseradish that would really water your eyes. Strawberries were they were pretty good. There's dessert. Here we are sitting down for supper. We had trays. You can see some of the food stuck to the back there. We had trays that we could position on our laps, Velcro, and then set our food in them. As Steve pointed out, this zero gravity adds new meaning to the term pass the potatoes. They float them all the way across the cabin. The menu was quite varied and really pretty good. People accused me, we had color code, and people accused me of always having my color on everything.
Exercise was part of our daily routine on orbit, just like it is back here on Earth. Getting set up on the treadmill takes a little bit longer on orbit, but it feels just as good to quit. And our sleep arrangements looked a lot like summer camp. A little bit of bunks here and there. 2 of us slept anchored to lockers, 2 of us slept strung across the room, and 2 of us slept on the wall. And you can notice that in zero G, when you relax, your arms tend to float up. It was very comfortable.
We didn't always sleep with the night light on.
Well, we chose a sunset as to all good things must come to an end, and you can see some thunderstorms sticking up in the limb of the Earth there on the horizon. Sunsets from space are absolutely beautiful. You've heard us say this many times. It's still true, and it's difficult to capture all the color on camera. We had a good flight, and we came home. Here you see the RCS jets firing as the tracking cameras at Edwards picked us up a little over 100,000 feet. We had some test inputs that were put in by the computer, 11 sits tests throughout the entry to get data to verify the aerodynamics of the orbiter. And when those tests went in, it caused quite a bit of jet firing. When the last test was over, at about 0.9 Mach, I took over manual control of the orbiter and then guided it around the head and alignment circle to a final approach. As we turned on final here, you'll see some streamers pull off the wingtips as we get the final alignment. Here we're about 13,000 feet picking up speed. We're about 280. Push over into a 19-degree glide slope. Somewhere around 2,000 feet, 1,800 feet, we begin to flare the vehicle out to a more nominal 1.5-degree glide slope. At 300 feet, Mike put the gear down. That was a good sound to hear that coming down. And we bring it in then for going down closer to the runway where we break the rate of descent even further. The orbiter flies extremely well. I was quite pleased with it. It's a good, solid handling airplane. Started in for a landing that we were all proud of, and about 185 knots, started the nose down. The nose went down per normal. To us, it seemed like it really banged down hard, but it always does because of the negative angle tack you have. Braked it to a stop. Took us, I guess, 25 or 30 minutes to get the orbiter shut down. The thing about the orbiter is you're not through flying until you get it all shut down. That takes a while. Got our legs under us and came out and looked at it. It was an extremely clean airplane, as you've probably seen in the pictures. It came through in fine style, minimum tile damage, and the systems on board were in extremely good shape. So we're real proud of it. It's a welcome addition to our fleet. We now have 3 airplanes in our national transportation fleet, and I think we're in a position now that the agency can really go get serious about flying.
Okay, I think we have some slides.
Sunday, April 12, 1981, Kennedy Space Center, Florida. The Space Shuttle, 14 stories high, 2,000 tons, poised on the pad for its maiden flight. This is Columbia, the spaceship that will orbit the Earth. Its external tank, it holds over 500,000 gallons of fuel for Columbia's 3 main engines. And the solid rocket boosters, the largest ever used on any launch vehicle and the first to be employed in a U.S. manned flight. At liftoff, the solid rocket boosters, together with the 3 main engines, will unleash more than 6.5 million pounds of thrust needed to launch the world's first reusable spacecraft. Never before has a winged vehicle been launched like a rocket, orbited the Earth, returned through frictional heating in excess of 2,500 degrees, and landed, still aerodynamically sound, to be launched again and again. If it succeeds, the space shuttle will truly be a remarkable flying machine. There are many other goals to be reached during the 54.5-hour mission that lies ahead. 144 test objectives are planned for the flight. These objectives could not be achieved without an astronaut crew. The commander, John Young. The pilot, Robert Crippen. Young has already been in space 4 times for a total of 533 hours. He is the most experienced astronaut flying today. Although Crippen has over 4,000 hours of jet aircraft flying time, this will be his first time in space. The astronauts make their way across the access arm toward the shuttle in the pre-dawn hours before launch. An American spaceship has never carried a human crew on its maiden voyage. At the Launch Control Center, 3 miles from the pad, final steps are being completed in the countdown. Final preparations are also being made in the Mission Control Center in Houston, where control of the flight will switch once the shuttle clears the tower. There has not been a manned launch from Kennedy Space Center since the Apollo-Soyuz test project in July of 1975. With this launch, Young and Crippen, launch controllers at the Cape, and flight controllers in Houston will experience the most dynamic, fast-paced series of launch events ever undertaken in the space program, all in less than 9 minutes. The most challenging ascent profile ever to be flown by a space vehicle. Photographers, film and television crews, plus newspaper and magazine writers from around the world, nearly 2,700 of them are here to cover the launch. In addition, approximately 600,000 spectators line the coastal area near the Kennedy Space Center. Arriving by every mode of transportation, they have come from every state in the Union and many foreign countries. The promise of a rebirth in America's manned space program and the dawn of a new era in space transportation awaits.
15, 14, 13, T-minus 10, 9, 8, 7, 6, 5, 4. We've gone for main engine start.
Roger, roll.
The roll will put the shuttle on its precise heading toward an imaginary target in space.
Roll program complete.
Roger, roll complete.
Status, Fido. Go. Booster. Go. GNC. Go. Eagle. Go. Go at 40, Capcom.
Columbia, Houston, you're go at 40.
The shuttle is now 40 seconds into flight.
Roger, Columbia, on the nice ride. You're lofting a little bit. You'll probably be slightly high at staging.
Negative seats.
Columbia, you're negative seats.
Should anything go wrong, the shuttle is now too high for the astronauts to use their ejection seats.
Columbia, you're go for SRB step.
We see SRB step, flight.
Roger, on a step.
103, converge, flight.
Bet. Capcom, let's tell them all the calls are going to be a tad early because of the hot first stage. Columbia, you're looking a little hot. All your calls will be a little early.
Okay. Okay, map looks good here.
Stand by, press to MECO.
Columbia, stand by, press to MECO.
Mark it.
Mark, press for MECO.
Roger, press for MECO.
The shuttle can now continue toward MECO, main engine cutoff.
They like the VAP, Eagle, ECOM. Let's go, flight.
Capcom, VAPs go.
Stand by, negative return.
Columbia, stand by for negative return.
Mark it.
Mark, negative return. And your VAP is good.
Outstanding. Sure is, we can confirm it. What a view.
And single engine rota, flight.
And Columbia, your single engine rota.
Columbia can land safely at the Naval Air Station in Rota, Spain, even if 2 of the 3 main engines should fail. Right now, the engines are generating over 42 million horsepower.
MECO 25, 6,
MECO.
0, up at 220.
Roger, MECO.
And we got MECO confirmed.
MECO, Roger, Columbia, MECO. Right on the money, nominal.
Main engine cutoff. Columbia is now in space, traveling over 18,000 miles per hour.
Okay, we got step.
Roger, we confirm the step, Columbia.
The external tank has just been jettisoned and is now falling away from the shuttle back toward Earth. The tank will break up as planned over the Indian Ocean when it comes into contact with the atmosphere. Shortly, by firing the OMS, Orbital Maneuvering System engines, Columbia will achieve orbit. Then one of the most important tests of the mission will be attempted, opening the payload bay doors. The doors must be opened before the end of the 6th orbit to expose the space radiator cooling system. If the radiators cannot be exposed, heat collected from the onboard electronics cannot be released, and the astronauts will have to return home. The OMS burns are successful. Columbia is now in orbit, circling the Earth at an altitude of approximately 150 miles. The payload bay doors will now be opened.
Okay, the port door's coming open now.
Roger, copy.
Well, you're missing one fantastic sight. Boy, that is really beautiful out there.
We appreciate those updates.
Both doors have been opened. The radiators can be deployed to begin dissipating the heat.
The doors are all opened up and hunky-dory. Glad to deploy it right on time.
And the radiators look good.
Okay, we want to show you our own pods here. We do have a few tile missing off of both of them, off of the starboard pod, 3 tile and some smaller pieces, and off the port pod, looks like I see 1 full square and looks like a few little triangular shapes that are missing, and we're trying to put that on TV right now.
Roger, Crip, we can see that good.
From what we can see of both wings, tops and leading edges, though, all those are fully intact.
Within minutes, an assessment is completed on the impact these missing tiles could have on the remainder of the mission. At a news conference later in the day, Flight Director Neil Hutchison answers questions from reporters.
But you asked me if I knew where there were any other tiles that might be loose. The answer is no. And quite frankly, we're not worried about any other tiles being loose.
At this writing, is there anything at all that would lead you to say you might not go for a full duration mission?
Nothing.
Columbia, Houston, you guys did so good, we're going to let you stay up there for a couple of days. Your gopher on orbit.
Spacecraft wants gopher on orbit. This thing is just performing just outstanding.
Roger, we agree with that. And Columbia, Houston, just for your information, you dropped those SRBs right on target, and they were floating just the way they ought to be, and the boats were getting ready to fish them and bring them back.
Okay. The ride that they gave us was pretty neat.
The solid rocket boosters, which separated from the Columbia as planned 2 minutes 11 seconds into the flight, landed on target in the Atlantic Ocean, 151 miles downrange from the launch site. After being towed back to Kennedy Space Center, both boosters will be refurbished and used again in a future shuttle flight. The 3rd and 4th OMS burns are also successful, raising Columbia's orbit to an altitude of approximately 172 miles. For the first television transmission from inside the spacecraft, the crew will give a status report on the mission.
The flight so far has gone as smooth as it could possibly go. We've done every test that we're supposed to do, and we're up on the timeline, and the vehicle has just been performing beautifully, much better than anyone ever expected to do on a first flight, and no systems are out of shape. And it's delightful up here in zero gravity, might add. Of course, we owe this to a lot of people, so we certainly want to thank everyone who has helped get this thing airborne, and can take great pride in it's doing so well right now. Okay, we're switching over to the aft camera here. I'd like to echo John's words as I usually do. I guess being the so-called rookie on this flight, I had a thrill from the moment of liftoff all the way up to what we're doing now. It's really been super. The spacecraft has worked as advertised all the way along. I think we've got something that's really going to mean something to the country and the world. This vehicle is performing like a champ, like all of us that have worked so long on it knew that you would.
Okay, sir, we appreciate those comments.
I guess that does it.
That was a good time, and I think you must have practiced. We're just about to lose your ghost song.
Just accident.
Just accident, says Robert Crippen. None of the other events of the day have been accidental. Every test, liftoff, SRB separation and recovery, ET separation and impact, 4 OMS burns, payload bay door latch opening and closing tests, radiator latch deploy and stowing tests have all been successful.
I guess we owe you guys one super attaboy for today. This is fantastic. You worked through a pretty long, hard day, and you're essentially right on schedule, which is going to be close to being a first sort of spaceflight biz, I think, for first day activities. It's sure been fun working with you today, and we look forward to seeing you in the morning. I hope you get a good night's rest.
Okay, you guys did super work today. See you mañana.
Roger, thank you. See you tomorrow, guys.
Well, many, many hours went into this thing. A job well done by the shuttle space team. We can't say that she's sleek and lean, but I'll tell you right now, she's a mean machine. The Columbia, not the kind you smoke. This here's a bird.
Morning, Columbia. Welcome to day 2.
All right. Appreciate that super wake-up music this morning. Well, we sure enjoyed it. Missing a good breakfast.
Today, the astronauts will test onboard systems and also review procedures for tomorrow's landing. A test of the flight control system is conducted by John Young. The flight control system operates Columbia's aero surfaces, the elevons, body flaps, rudder, and speed brake. These surfaces are useless in the vacuum of space, but will be essential tomorrow when the shuttle lands. This will require precision maneuverability, which the aero surfaces provide. Payload bay door cycling tests help ensure that latching and closing procedures can also be done before entry tomorrow. As with every mission, many pictures of the Earth are taken by the astronauts. Over 500 on this first shuttle flight. Active volcanoes, cloud formations, alluvial fans, giant whirlpools over 15 miles in diameter, sand dunes 1,500 feet high, running unbroken for hundreds of miles. The high Himalayas, where mountain peaks reach 24,000 feet. And one of the most remarkable space photographs ever taken of the Earth, an area in Iran exposed to wind erosion, which has resulted in these breathtaking silt and sandstone formations that look more like a painting than a desert. After lunch on the second day, the astronauts receive a phone call from the Vice President of the United States, George Bush.
How's it going up there? Everything rocking along all right?
Spaceship is just performing beautifully.
Well, it's great, and everybody views it, I'm sure, just as the forerunner of great things to come. I think your trip is just going to ignite the excitement and the forward thinking from this country, so I really just wanted to call up and wish you the very best.
We appreciate it, Mr. Vice President.
The crew also don and check out the ejection suits they will wear during entry. Young, Crippen, and Columbia pass every test. They are ready for the final phase of the mission, entry and landing. April 14th, 1981. NASA's Dryden Flight Research Center on the edge of Rogers Dry Lake Bed in California. A recovery convoy of 24 vehicles and more than 100 personnel are assembling here to power down Columbia after landing. Enormous crowds are also beginning to arrive. A string of traffic 6 miles long waits to enter the base. Thousands more are already here. Close to 500,000 people will eventually be on hand to see the landing. On board, the astronauts suit up for entry. The ascent and orbital phases of the mission have gone extremely well. Now the final phase must be completed. Before that begins,
Columbia, you have a go for payload bay door closing.
The doors, which have been open a total of 47 hours during the flight, must now be closed. Then, using the RCS thrusters, Columbia will maneuver into deorbit burn attitude, head down and backwards, fire the OMS engines one last time, and descend into the Earth's atmosphere.
Nice and easy does it, John. We're all riding with you.
Columbia is out of contact during the OMS burn. Mission Control will not know if this burn was successful until they are in communication with the spacecraft over Australia. It is now over the Indian Ocean on the other side of the world. But from that distance, the burn must be precise, so that later, Columbia will hit the lake bed target in California.
Columbia, this is Houston through Yargady. We're standing by.
Burn was on time at nominal residual 110.
Columbia is now committed to entry. With an RCS post-burn maneuver and several firings, it is oriented to a heads-up, nose-first attitude headed toward entry interface. This is where the atmosphere begins, at approximately 400,000 feet. From that moment until the shuttle reaches 165,000 feet, it will be in communication blackout, out of touch with mission control for almost 20 minutes. The landing site is almost 4,400 miles from entry interface. Chase planes are preparing to take off. One will call out altitudes and check Columbia for any damage just prior to landing. When the shuttle touches down here, it will be traveling at 216 miles per hour. Right now it's going more than 17,000 miles per hour. Before it lands, it must slow down, lose energy, and it must survive the intense heat caused by traveling through the atmosphere at such a high rate of speed. Several S-turns or roll reversals are used to slow down and maneuver Columbia through the atmosphere. This one is done at 256,000 feet when it is traveling at more than 26 times the speed of sound. This one is done at 208,000 feet. During these two roll reversals, entry heating is most severe, with temperatures reaching 2,500 degrees some places on the vehicle. The aluminum skin will melt at 320 degrees. The silicate tiles must insulate the vehicle from the tremendous heat. Since there is no test facility on Earth to simulate the aerodynamic and structural environment Columbia is in right now, only calculations could be used to predict what would happen during this phase of the flight. The predictions and calculations had to be right.
Hello there, Houston. Columbia's here.
Hello, Columbia. Houston's here. How do you read?
Clear and clear, and we're doing Mach 10.3 at 180 AS.
And we couldn't agree more, John. Your state vector's good. We've got good data in-house.
Okay.
The entry trajectory, velocity, and position look good. Columbia is heading for home, now only 470 miles away.
More left RCS, but okay.
Right, we're showing a roll. And John, we're showing you rolling right. Looking good.
Right, normal roll.
We're showing crossing the coastline flag.
Columbia, we show you crossing the coast now.
Right, yeah. We can come.
The shuttle is first sighted at about 100,000 feet with a long-range camera from Anderson Peak, California.
What a way to come to California.
In flight photo, I still look perfect right on the nominal.
Roger that. Out of 112K, 4.8 Mach.
We're seeing this in a row.
We see Delaz 21 degrees.
A roll reversal is done over Bakersfield, California.
Oh, that's beautiful.
Chase has a tally.
Roger, checking.
And we're seeing 1.3 Gs coming around the hack.
Roger that.
The astronauts are making the final turn to line up with the runway.
Columbia, you're really looking good. Right on the money. Right on the money. And turning on to final, your winds on the surface are calm.
I got a win.
You're right on the glide slope, Columbia.
Yeah, clear, John.
Looks real good underneath. Everything looks real good.
Chase reports no tile or other damage is evident underneath the shuttle. Columbia's altitude is now just over 5,000 feet.
Pretty clear.
Without power, Columbia must land. It cannot make another attempt.
You're coming. You're down. Feet. 40, 30, 20, 10, 5, 4, 3, 2, 1, touchdown. Those gears, 10. 5, 4, 3, touchdown. Look it off, skipper. Columbia's on the roll.
Welcome home, Columbia. Beautiful, beautiful.
You want us to take it up in the hangar, Joe?
We're going to dust it off first.
This is the world's greatest all-electric flying machine, I'll tell you that. It was super.
Okay, convoy's on its way.
Convoy on. We'll stop on the Columbia. We'll stop.
The maiden voyage of Columbia has been a success. The astronauts and the vehicle have met or exceeded all 144 flight test objectives. The integrity of all the systems, propulsion, avionics, structural, flight control, power, and thermal, have been affirmed. John Young's comments after returning home.
I can't tell you what a tribute that is to the American working man and the American working woman, too. You can't imagine the variety of people who worked on this vehicle, from all walks of life, all capabilities and limitations. It's all due to their individual efforts. They proved that they can do the job. They proved it for the world to see. And I'm mighty proud to be associated with folks like that.
What a tribute indeed. The Columbia represents an achievement in aerospace technology and development never before realized in the history of manned spaceflight. It is our basic building block for the future.
It's what we've been trying to do for the last 10 years. We've got a vehicle with a payload performance that will allow us to do that, much cheaper than we've been able to do it before. It will immeasurably improve the defensive capability of the country. It will help develop space science and technology. When we get operational, the space shuttle will be able to do in 5 to 10 years what it would have taken us 20 to 30 years to do otherwise. We couldn't do it if we didn't have the space shuttle and that payload capability. And the sooner we do those things, the better off the country's going to be.
A revolutionary new era in space transportation has just begun. Routine access to space. Welcome to the future.
There it is.
Where?
It's right up, right above us.
Oh, wow. Bruce.
Wow, that's so cool seeing that so close, you know?